kirimkan ke email yang sudah didaftarkan oleh Bapak Ibu. Kira-kira jelas atau tidak ya? Yeah. Okay, so without further ado, I'm going to hand over today's meeting to Miss Weni Dwi Pratiwi, SPD MS. Miss Weni, the time is yours.
Hi, Michael. Welcome back to our agenda today, which is the workshop on mathematical proving. Like we have planned that we do have some assignment for the participants to do today. But before that, I think you want to give some explanation on how we do the task or the introduction about the assignment. To all, yeah.
Yes, correct.
Can I please allow me to read your short CV, because some of the participants who were not attending the yesterday conference.
You're welcome.
Baik, Bapak Ibu, saya bacakan sedikit CV singkat dari Profesor Michael de Villiers. Michael de Villiers has worked as researcher, mathematics and science teacher at institutions across the world. He studied at the universities of Stellenbosch, Free State, and Cornell University, United States of America. He taught at the University of Stellenbosch from 1983 to 1990, and then at the University of KwaZulu-Natal, from which retired from at the end of January 2016. He has subsequently been appointed Professor Extraordinaire in Mathematics Education at the University of Stellenbosch. He was editor of Pythagoras, the research journal on the Association of Mathematics Education of South Africa, and was vice chair of the SA Mathematics Olympiad from 1997 to 2015, but is still involved in the setting of rounds 1-2. His main research interests are geometry, proof, application and modeling, problem solving, and the history of mathematics. I think that's all. Actually, Professor Michael has a very long CV, and he has also published some books, remarkable books. And one of the assignments that we want to do today is taken from his book, Rethinking Proof of Geometry. Is that right?
Correct.
Okay, I think we should start. So the Zoom is now yours. Professor Michael de Villiers from University of Stellenbosch.
Thank you, Winnie. Let me share my screen. Now I need to find Sketchpad and share. Now let me just see if the other one is showing as well. I hope is it showing the worksheet there as well on your side, or is it just showing the dynamic geometry sketch there?
I think on my screen only the sketchpad.
Only the sketchpad. So I need to. I wonder why. Can I go to new share so I can add something to that? Let me just add that. There it's showing now, and does it show both of them, or is it only showing one? It's only showing the worksheet. Doesn't show the two alongside.
Do you want to show
Um,
the sketchpad and the worksheet and the same page? Is
Yeah,
that what
do I
you mean?
need? Well, maybe I should select both of them. Let me, can I? Okay, share two. Now it should work. Let's see.
Oh, yeah.
There we are.
Yeah, that's
There we
nice.
are. Okay. Okay, let me just move the one a little bit out of the way so we can both of them at the same time. I see there's a little bit of lag in the presentation, but hopefully it is clear on your side. Is it clear on your side?
Yeah,
Where-
the
Is it clear?
the sketchpad on my left, and then on the right side is the worksheet.
Is the worksheet,
Yeah,
yes.
yeah.
I hope everybody who is present has a copy of the distances in an equilateral triangle worksheet. And I presume that everybody has been able to download and install Sketchpad to be able to open the sketch. Am I correct? Or are there some people who didn't have time to do that?
Can I confirm all the participants? Baik, Bapak Ibu, apakah semuanya sudah mendownload Sketchpad dan sudah punya worksheet supaya kita bisa mulai?
Saya sudah semua, Bu. Sudah
Baik,
download
terima
semua.
kasih, Bapak. Oke, so we can start.
Okay. If I can talk about this activity from my book, it is an introductory activity intended to acquaint learners at high school, but I have also used it with teacher training to acquaint them with the explanatory function of proof. And if I can read to you, and unfortunately I will have to move it on my side to be able to read. The problem is the following. A shipwreck survivor manages to swim to a desert island. As it happens, and this is not very realistic in the real world, but we are assuming here that the island closely approximates the shape of an equilateral triangle. She soon discovers, the shipwreck survivor, that the surfing is outstanding on all three of the island's coasts. So she crafts a surfboard from a fallen tree and surfs every day. Where should she build her house so that the sum of the distances from a house to all three beaches is as small as possible? Now, it is assumed here that she visits each beach with equal frequency. We are assuming essentially that the surfing is equally good every day on each of the beaches, which is not very likely in the real world. But it is a fun problem that children usually and students usually enjoy. Before you proceed further, locate a point in the triangle above at the spot where you think you should build a house. If I can ask anyone from the audience, where do you think that point should be located so that the sum of the distances from my house to all three beaches is as small as possible? And preferably somebody who hasn't done the problem yet. Any suggestions? Where in the triangle should that point be located? Getting no answer, I will say what the normal response that I would often get from students is they would likely guess the center. That is where the sum of the distance from here to each of the sides would be a minimum. And the center, they might say the centroid, or they might say the in-center. Of course, they're all coincide with the same point when we have an equilateral triangle. After students have done something like that, I get them to open the sketch, distances.gsp, supplied by your teacher, and then they are asked to drag the point P to experiment sketch. And then they are told to double click the button, etc., to show the distance sum, drag point P around the interior, and what do you notice about the total sum of the distances? And I will now go to the sketch, which should hopefully appear there. As you can see, there's a copy of an accurately constructed equilateral triangle, and students are asked to drag P around in the middle to see what happens. And I hope people are following me and doing similarly in the workshop. As you can see, as we drag it around, these distances, shortest distances, which are perpendicular, I haven't indicated the perpendicular distances there. You can see that they vary as we move P. If I move in that direction, the other two distances approach 0, whereas the distance H2 becomes bigger and bigger. Now you'll see there that you are asked in the worksheet to show the distance sum. Now, if we click on that, it will automatically display the distance sum there. And what happens if we now drag P? What do you notice?
Same
No
result.
matter, yes?
Ya, Bu Dwi, silakan.
Yes, please speak. What do we notice?
I noticed that the sum of the what's this? H1, H2, and H3, it's equal.
To a constant value, correct. Correct. It doesn't change. It only changes if we change, say, increase the size of the equilateral triangle. As you can see there, if I change the size of the equilateral triangle, it changes, but as soon as I stop moving or changing the size of the equilateral triangle, and I go back to dragging P, the sum of the distances remain constant. And my experience usually has been children and even adults, teachers who have not seen the result. This is a familiar result to people who work in geometry, but it is not that common in ordinary geometry textbooks. It usually comes as quite a surprise to find this, because they expected the minimum to be at P. P is at the center, rather than finding now it doesn't matter where it is placed, that distance remains constant. You will see that the second question is there: drag a vertex of the triangle to change the triangle size, then again drag point P around the interior. Notice now. Well, we've already done that. We've seen that if we change the size, the sum of the distances change, but as soon as we stop changing the size and we go back to dragging P, then the sum remains constant. Question number 3, what happens if we drag P outside the triangle? Well, as you can see there, now the sum of the distances is no longer constant. Of course, in the real world context, you may recall we were talking about the desert and that she wants to build a home on the island, it sure would not it sure would not make any sense to build her house outside the triangle, because then it would be in the ocean. So clearly, this is not a solution to consider. Now, what I would like people to do is to formulate a conjecture. Organize your observations from 1 to 3 into a conjecture. Write your conjecture using complete sentences. And if I can perhaps have one of the participants, once you've written down your conjecture, read it. I will give you a minute or two to think carefully about it.
Okay. So for all the participants, please make your conjecture based on this problem. So we have question 1 to 3. And once you have done exploring the sketchpad, then you may have conjectures about this problem. A minute or 2 minutes?
2 minutes should be sufficient, I hope.
Okay.
It's not very hard. Let's say 2 minutes at most. I'll keep an eye on.
Baik, Bapak Ibu, apakah mengikuti instruksi dari soal ini?
Ooh. I just got a message here that my internet is unstable,
Really?
but it's gone away now. So let's hope it doesn't cause a problem. We've been having problems with power cuts, and we've also had some rain, etc. So I'm keeping my fingers crossed. But the message has gone away just now, so let us hope it doesn't interfere.
Yeah.
There's a minute left, I think.
We still have 1 minute left. Can I explain a little bit the problem with bahasa, maybe?
Sorry, must I explain something to you, or you explaining something?
Explain to all the participants in bahasa about the problem. In bahasa Indonesia, in Indonesia.
Oh,
Bapak
okay.
Ibu, oh, we have one answer.
Mm-hmm.
Mr. Safrudianur, do you want to speak directly?
Okay, I'm waiting.
Okay, this is my conjecture.
Yes.
If P is a point inside the triangle ABC, the sum of the distance of P to line AB, P to line AC, and P to line BC is fixed.
Okay. Can I just write that down? If I heard you correct, I'm just going to type. Normally I would write. Unfortunately, with a pen on a tablet, I'll have to type, and I type. If we have a triangle, or in a triangle ABC, let me just take a shortcut here. In a triangle ABC, oops, why is it not typing? ABC. Oh, somehow it's not typing.
Because your internet is...
There. Yeah, in a triangle ABC, the sum of the distances, I'm just going to say to the sides, sum of the distances to the sides are constant. Is that what you said? Do you want to change that, or are you happy with that?
Distance P. P, there's a point P. P is a point inside.
Yeah, the sum of the distances from the point P, sorry. The sum of the distances
Of
from a point P. We could say an arbitrary point to
Yeah.
say it doesn't matter where it is if we want to. Is that essentially what you're?
Yes, yes. But point P is inside the triangle.
Yeah, yes, yes. The sum of the distances from an interior point.
The interior
Yes,
point, yes, yes.
we saw that
Interior
if we
point.
dragged it outside, it wasn't true. But any comments from other participants? Are they happy with that conjecture?
We have one more response from Leonardo Jonathan Sinarico in the chat box.
Okay. Oh, in the chat box.
If the P is inside the triangle, the degree that formed by P, it would stay the same, namely 120 degree each for each. It makes the sum of the distance stay the same.
Yeah, yeah. Yeah, in other words, the angle surrounding P would be 120 degrees each. Yes, that's an interesting conjecture, which is obviously very easy to prove because this angle is 90 degrees, that one is 90, this is 60, which from the sum of the angles immediately means that's 120. So yes, that's correct. I see some other people have written up my P is inside the triangle, the sum of the distance is fixed. I see, yeah, it's useful in the chat. I can see what some of you have written. I have some concern with your conjecture. In a triangle ABC, are you saying any triangle ABC?
Any triangle, any triangle.
In any triangle, the sum of the distances from an interior point P to the sides are constant. Do others agree with that?
Baik, Bapak Ibu, apakah setuju dengan konjektur dari Bapak Safrudianur yang mengatakan bahwa ABC ini adalah segitiga sembarang? Adalah semua segitiga.
Segitiga sama sisi kayaknya itu. Anda harus enggak?
Yeah.
Equilateral.
We need to say an equilateral. We haven't explored. It might be true. It might be true that for a general triangle, it is also the case that the sum of the distances from an interior point to the sides is constant. My grammar, that should be is constant. The sum is singular. But we need to say here, and because this is what we observed. Remember, we were told that this was, oops, let me just correct my spelling, that this was an equilateral triangle. That is very important to state that. For what we have observed, we have not yet looked at the generals when the triangle is not equilateral. So that is an important aspect that needs to be stated. It may be true, but at this stage we have not yet explored that or have any reason to think that it would necessarily be true. It's a good conjecture, but we'll have to explore that. Is everybody happy with the conjecture? Let us now proceed to explain why the conjecture is true. Now, if you go back to the worksheet, you will see that I have a little bit of a spiel there at the beginning. Distances in an equilateral triangle explaining. Notice I'm deliberately using the word explaining rather than proving, but essentially what we are going to do is prove the result. But I think for beginners, if we're working with young children, it is more meaningful and sensible to them to focus on the explaining aspect. So I'm just going to read from the text there. You are no doubt convinced that the total sum of the distances from point P to all three sides of a given equilateral triangle is always constant, as long as P is an interior point. You remember you saying it on the inside. But can you explain why this is true? I want to repeat that, but can you explain why the distances is constant? Although further exploration on Sketchpad or other software may succeed even more of the truth of your conjecture, it only confirm its truth without providing an explanation. For example, the regular observation that the sun rises every morning does not explain why this is true. One has to try and explain the observation of the sun in something else. For example, the rotation of the Earth around the polar axis. Recently, well, this is not so recently, this is about 20 years ago, or more actually, a mathematician named Feigenbaum made some experimental discoveries in fractal geometry using a computer, just as you have now used Sketchpad to discover your conjecture about a point inside an equilateral triangle. Feigenbaum's discoveries were then later explained by Lanford and others. Here's what another mathematician about all this. And I'll just read that quote. Lanford and other mathematicians were not trying to validate Feigenbaum's results, any more than, say, Newton was trying to validate the discoveries of Kepler on the planetary orbits. In both cases, the validity of the results was never in question. What was missing was the explanation. Why were the orbits ellipses? Why did they satisfy these particular relations? There's a world of difference between validating and explaining. Now, explore an explanation. We are going to logically explain it. And if you can follow through with me in these steps, the first step there is press the button to show the small triangles in your sketch. I will go back to the sketch. So press this button to show those small triangles. Okay. I'll go back here and then it says drag a vertex of the original triangle. Why are the three different labeled A? I think that's easy to answer. Why are they labeled A?
Equilateral. Because
They are equilateral. We are given that it's equilateral. That's easy. That's obvious. Now the next one, I will give you a minute for that. Number 6, write an expression for the area of each small triangle using the variables H1, H2, H3, and the equal side A. I will give you about a minute for that. That is fairly easy. Well, for the rest, you can continue. Then add the three areas and simplify your expression by factorizing, essentially, by taking out any common factors. And then comes the crucial question, how does the sum in number 7 relate to the total area of the equilateral triangle? Equation to this relationship, and you can use A for the area, for the total area of the equilateral triangle. Use your equation from A to explain why the sum of the distances to all three sides of the triangle is always constant. So I will leave you with that for a short while to think about that, and I would like to have some responses from you regarding that. I will perhaps increase the size here so that I type in some of your answers here. I'll just move this a little bit out of the way. So I have some space on this side. I would like you to proceed now with number 6, right up until number 9. You write it down on a piece of paper or just in your mind, but it's probably better writing it down.
Okay, we can start to work number 6 to number 9. You can write down your answer in the chat box, or you can use just paper, and then you can show your work.
I see somebody has said the small triangle is a isosceles triangle. Not necessarily. If you look at this yellow one, clearly this side is not equal to that one. Of course, it can be an isosceles triangle, but it's not necessarily. Remember, P can move around. So depending on where you've placed it, it may look, your point P is there, this yellow one. This side looks equal to that, but obviously it need not necessarily be, as you can see there. So those 3 triangles, the yellow, the gray, and the brown one, they will change shape.
Two participants respond to.
Somebody has already written down. Obviously, all you need to do for question 6 is use the area formula of a triangle, base times height, which is, I'm familiar to usually primary school children, if I'm correct. In South Africa, I think they learn the formula in about grade 7.
One of the participants already answered number 6 in the chat box. We have Nur Zahwa.
Leonardo, I see, yes, correct.
And Leonardo, I think, answered number 8 because he already expressed the relationship with A.
He's already actually simplified. He's done number 7 as well, correct? Now you just have to do question 8 and 9. Now, unfortunately, the chat box doesn't allow for nice presentation.
Yes.
It doesn't allow you to put it in a normal mathematical format with fractions and subscripts, etc.
Is there anybody who wants to answer number 8 and 9?
Because this is the crucial part of the explanation. How does the sum in number 7 relate to the total area of the equilateral triangle? That's easy. Write an equation to show this relationship. Use A for the area of the equilateral triangle. I see Safru Diana Nur has written H1 is equal to A star. What does it mean by A star square?
Multiply. Star is multiply.
Oh, so A multiplied by the square of 3.
I replace it. It should be
Yeah, what we're saying in number 8, yes. I'm not sure. Yes, Leonardo, correct. Correct. Yeah, the total height is equal to the sum of the 3 distances. That's one way of looking at it. It's not exactly what I had in mind for number 8.
Okay.
But I will explain. It's essentially that the total height of the equilateral triangle is equal to the sum of the 3 distances. Now, how does that explain why the sum of those distances are constant? Number 9, very quickly. Well, if we have an equilateral triangle, the distance for a fixed equilateral triangle is, of course, the height from this vertex to this side is the same as the height from here to there, because the equilateral triangle is symmetrical. It doesn't matter. So it has a constant height. So once we have that the sum of the 3 distances is equal to the height of the equilateral triangle, we've essentially shown that it is constant. So that is already an explanation. Let me perhaps just write that out to summarize that. Basically, we have that the 3 distances are equal to, and I will also just take, 0.5 times A times, well, let me perhaps use the facility that I have here. So I will say H1. And let me just exit there, plus, and I'm just writing 0.5, and not to have to use a fraction as well. I'll correct that just now. And is it visible on your side, or should I increase the size?
No, that's good.
Is it good? We have that a half A times H1 plus a half A times H2 plus a half A H3. That would be the sum of the 3 areas. Now that is obviously equal to the total area of the equilateral triangle, which we're just calling A, or as Leonardo did, it is also equal to 0.5. Well, let me just save time and paste that text in, and I will just edit it. That is the same as, call it big H. Oops. That's the same as the area of the large triangle is half of the base times the total height of it, which I'm just calling big H. Now, we can do it in either way. I will show both ways. We can summarize here by, or simplify on this side, by taking out a half A on this side, which, let me just type that, half A, and I will, just to save time, just select all of that. Usually I would write this out on a blackboard or on, unfortunately with this computer, my tablet doesn't work. I haven't got software that connects it. So I would normally write it out, which will go quicker than me typing it, is equal to A. I will just leave it like that for the moment. We'll come back to what Leonardo observed. So I could then write this simply as that implies H1 plus H2 plus H3. Oh, I see I've got a plus sign there. I meant to
Yeah, that's mistake.
that is equal to 2. Well, let's put a fraction in here. Where's my fraction? So I have 2a over a. Now, what do we notice here? Well, we have on the right-hand side, the area of the equilateral triangle is fixed. And so is the side. So the right-hand side is a constant. By saying it's a constant, we mean it is fixed. It won't change. So if the right-hand side is constant, it means that the sum of these three variables, because we see that they are variables, that they are constant. So that effectively proves the result. Of course, if we look at the top relation, that's the same as what Leonardo mentioned, is if we just divide it right through by a half a, then we just get that that is equal to h, which is what Leonardo observed. And the height of the equilateral triangle is always constant and change for a fixed equilateral triangle for a desert island, if you like, which means that the sum of these three distances has to be constant. And that, I think, effectively is a reasonable explanation for why that is the case. Questions on that at the moment?
So we can say that the sum of the distance from point P to the sides of each of the triangle is the same as the altitude of the big triangle.
Correct. We've just proven that, to use the terminology of deductive proof. We've proven that the sum of these three distances is always equal to the altitude, the height. It doesn't matter from which side we take the height. Or if we like, just to say that it's the same as 2 times the total area divided by A, which is an alternative way of looking at the same problem. I want to ask you something further. If we look at question 11, well, question 10 really relates to what we have already shown. Drag P to a vertex point. How is the sum of the distances related to the altitude of the triangle in this case? Well, if we now drag P to a vertex, let's say we drag it here, if it goes to a vertex, then obviously the distances H3 and H2 will become 0 because that is where those two sides intersect. So it becomes 0. I'm not going to, well, let me drag it right on top of it. As you can see there, it displays the distances equal to 0. And we now have that H1 is now the altitude. Okay, and the same is true, obviously, if we move to the others, the other two distances would be 0, and the distance, the remaining distance would simply be the altitude. That's just to confirm what Leonardo already mentioned there. Explain why your explanation in 5 to 9 would not work if the triangle was not equilateral. Remember, at the beginning, we just said in a triangle ABC, the sum would be constant. Well, if we look here, the first part of the argument would be problematic, because if it was not equilateral, this would not be a or rather not all three would be A, we would have A, B, and C, for example. And then we wouldn't be able to factorize it in this form, nor to into this form. This does not mean that it might not be true for any triangle ABC. But what this shows is that if it were true, we can't use the same argument. Okay. Does everybody follow me in that regard? Now, let us move to the next part of the worksheet. Well, I'm not going to ask you to write it. What I normally do is have students just write it out so that they have the explanation, the proof. Some history is perhaps useful. The result that the sum of the distances from a point to the sides of equilateral triangle is constant is known as Viviani's theorem. Viviani was a student of the 17th century Italian mathematician and scientist Evangelista Torricelli. Does anybody know anything about Torricelli? What is he famous for? I'm a bit of a history buff, so I like I like to test people's historical knowledge. Okay, I once did this workshop with students, and one student put up his hand and he said, "I know the answer." And he was sitting with his cell phone. He'd meanwhile Googled the name Evangelista Torricelli, so he could tell the whole class everything about Torricelli. I suggest that perhaps you can Google later, but I will just tell you briefly. Yeah, I will just tell you briefly. Torricelli is probably most famous for the person who invented the barometer, which measures air pressure. He was a pretty good scientist for his time. So he invented the barometer. He also designed pumps, water pumps when there was a big drought in Italy, using a series of valves and so on, which help people access water when the water table dropped particularly low in I can't remember what year, but in the 1600s. So he's quite famous, and he was also a fairly accomplished mathematician. But you can Google and read more about him and also about Viviani. Now, let us move to the question which we haven't answered. Construct any triangle ABC and an arbitrary point inside. Where should you locate P to minimize the sum of your distances to all three sides of the triangle? Now, since most of you are not that familiar with Sketchpad, I will rather do this myself, so you can just watch. I will construct an arbitrary triangle and a point inside, and then I will measure the distances and I will sum them, and then we will investigate the problem together, just to save time. I would normally do this with students that are used to Sketchpad, or at least have had some familiarity with it. It would take too long. So I'm just going to do it myself. I prefer the color blue. So let me just change the color there. Whoops, something strange is happening. Okay, so I'm just drawing an arbitrary. If you use GeoGebra, you construct it in much. And notice this is now an arbitrary triangle, which I can change the shape as I wish. Remember, the other one remained equilateral, no matter how I dragged it. Now we need to construct our point P inside. I'm not going to label it, but I'm simply going from that point to the sides, I'm now going to measure the distances. Let me increase the size of that a little bit, perhaps to 18. Is that clear? Is it showing on your side? Okay, so I have the distance from A to BC, as you can see there. So it moves closer, the distance smaller till it's on top of it. If I move away, and even move it outside, it gets bigger. So I can measure the distance to this side. And I will measure the distance to this side. Okay, but we want to find out where is the sum of the distances of these minimum. So we need to calculate and add them all together. I see it's not displaying part of my screen there. It's not displaying the calculator. Am I correct? Because I don't see the calculator there, but it will display it now.
No,
the
there is no
screenshot.
calculator.
Yeah, I don't know why it's not displaying that, a part of the screen, because it should be part of it. Well, now we have the $1 million question, and usually when I get this far, I ask students, well, what do you expect? And some students say it will remain constant, while some say it will change, and then I say, well, check what happens. Well, if I start moving the point A, not P in this case, we see, unlike the previous case, is it displaying on your side?
Not yet.
Ooh,
I don't
I
see
see
anything
it's not
changing.
displaying anything. Sorry, I see it's still displaying. I wonder why. Sorry, it's just displaying one screen at a time. Sorry, my mistake.
Only
here.
one screen, the one that we did.
I see. Okay. I need to look for that one, this one then. Okay. Let me get all three on again. Okay, you see, I'm not too familiar with working with the software. Now
Yeah,
it
this
should
one,
display.
I think the triangle.
Yeah, oh, sorry. Yeah, sorry, I should have noticed that it wasn't displaying. Apologies. Okay, well, I have constructed here an arbitrary triangle, as you can see here. Sorry, I'm not going to go through the steps again, but this is an arbitrary triangle, as you can see there, which is quite easy. I mean, I could redo the steps if you want. Do you want me to redo the steps quickly? I can quickly redo it if you like.
Yeah,
Or
maybe
is
it is
it okay?
better to redo it
Okay, I'll redo
because
it.
we didn't see the process previously.
Yeah. Now let me redo that. The labels will be a bit different, but it's the same process. Okay, it's quite easy to construct. You just use the segment tool in Sketchpad, and you then just, once you've clicked on it, you just drag it out. It's similar in GeoGebra. I think some of you probably know GeoGebra, which is a program that was developed a little bit later, but it uses the same idea. So this is now no longer equilateral. I can drag it into any shape, obtuse, acute angle, triangle, even a right triangle if I wanted to, etc. Now let's construct a point P inside. And now I will just select a side there and measure the distance to that side. As you can see there, here's the point E, and it displays the distance from E to FG. So if I move the point closer to FG, it becomes 0 if it's on it, or it increases as I drag it further and further. I'll just do the same for the other two sides, measure the distance, and I'll measure the distance here. And now you can see, just like we had before, as it move it around, the distances change. The question is, where is the sum of this a minimum? Now we need to use the calculator. Let's see if the calculator displays, you see, now it displays. Okay. I should have noticed when it didn't display the calculator. So I simply click on that and I sum them together in my calculator quite easily. And there I have the sum of the distances. And the issue is now, is it always constant? Well, many students guess that it remains the same. Some of you may have expected that, but unlike the case for the equilateral triangle, it no longer remains constant. We can change the shape of the triangle, and you can see it changes. Of course, now the problem has changed. Where should we place it now? So that it is a minimum, because now it is changing. Now, normally I leave this for students to explore a little bit. I say, well, drag it around and look where it becomes smaller and smaller. You know, if I drag it this way, clearly it seems to be getting bigger. Can you see that?
Yes.
If I
Yes.
drag it that way.
That's bigger.
Yeah, it gets bigger. If I drag it this, it's getting smaller. So maybe somewhere there, but yeah, it's getting bigger. Okay, there it's getting bigger again. So do you agree it looks like it might be here? Here where it is a minimum. Notice that it's below 9. There and here, if I drag it there, it's 9.43, etc. So where's it the minimum? Well, a good guess might be at that vertex. Okay, at that vertex. Okay, because now we have two of the distances 0, because it lies at the point where two sides intersect. Just going to leave it there. And we now have the minimum sum of the distances. Now, why should it be located here? Any explanation? Why not at this point or that point? Well, if we go back to what we did before, this would equal the height. And notice that this is the longest side. Okay, this is the longest side visually of the triangle. I mean, I can measure the distances if you're not sure. Measure the distance. FH is 17.53, and we can measure this one as well. That is 15.62. And this one, obviously, we can see is quite short. I'm not going to measure that. So clearly, this is my longest side. And this is a very interesting property of triangles, that your largest angle is always placed opposite your biggest side. In fact, Euclid proves that in his Euclidean geometry. And moreover, that is where you have your shortest height for a triangle. So the shortest height of a triangle will be here. Okay, from here to there. So if I measure the distance from here to there, it will just be 8.3. If I measure the distance from here to there, you will see that it is more. It's 9.31, you see, from F to GH. And if I measure the distance from here to there, it will be much bigger because this is the shortest side. Okay, so the distance from H to there, so the will be the largest here. And Euclid, in fact, proves this. I'm not going to do a proof normally in class with students. I would actually prove all of these because it's not very hard to prove, but that is a little bit cumbersome to do if I have to type it in, etc. But in Euclid, you can find all these results that I have referred to. let us move. How much time do we have left? Are we supposed to stop?
I think we already in the part, we don't have any breakout room. I think it is better just to speak in the whole classroom like this and big audience like this. So you can just continue and everybody can participate by raising hands if there are any questions about the material.
Okay.
We can just continue until.
Yeah, can we maybe do one more exploration and then discussion, or I would like perhaps just to do number 2A.
Yes.
Can we do 2A?
Yeah.
Open rhombus distance.gsp. Where should you locate P inside a rhombus to minimize the sum of your distances to all four sides? Let's go to our sketch again, our original sketch. The distances one. Do you have that open? If you have the distances one, you should have a little tag. Now, in your version, the tag might be at the top, which says rhombus distance. Do you have that?
Yeah, we have that already.
You should open up a little sketch like this, which has a rhombus already constructed for you. Now, obviously, that's an interesting problem in itself to ask students to construct a rhombus for themselves, etc. But to save time, because in this activity, the focus is elsewhere, that if they first have to construct a rhombus, it takes too long. So it's better to provide students with a ready-made sketch like this. Here we have a rhombus, which you can see I can again drag. I can change it into a square. I can make it bigger. I can make it quite, etc. We have our point P there. And let me make it a little bit bigger. And let's move it down here. So it is there. And the issue is, what can we say about the sum of the distances? Well, you can see it is displayed here, the sum of the distances. I will just make it blue and maybe increase the size. Just like we had with the equilateral triangle, we have that the sum of the distances remain constant. Why? Why is the sum of the distances constant here? Can you explain why it is true? I will give you a minute or so, 2 minutes to think about it. And I will give you a hint. Think about how we explained the preceding result for an equilateral triangle. Here we just have an equilateral quadrilateral.
One participant
All the
response, Ria
sides of
Febriani.
rhombus are the same.
Yeah.
Yeah, I mean, it's the same argument. I mean, if I will just copy here because I'm lazy. I will go back to the rhombus distance and paste that in there. Let me just hide that. I don't want that point there. It is essentially the same argument. I will just edit it a little bit so that you can see. If I, like we did previously, divide it into little triangles, and I will just show one triangle here. Suppose I divide it into, let's say, construct triangle interior. There we have a little triangle. I can draw 4 triangles just as we did before. And again, we can find the area of this triangle, area of this triangle, the area of that triangle, the area of that triangle. So in this case, we have exactly as before, we have the same argument. I will just paste this in here, except that we now have 4 distances. Let me just change that to, whoops, what has happened now? Okay, sorry, that has bamboozled me a little bit. Make that H and 4. Okay, as we can see there, the argument remains the same. Is it large enough on your side? We have that half AH1 plus half AH2, so we think of the distance there, we think of the distance here, we think of the perpendicular. That must be equal to the area of the rhombus, whatever the area is. I'm just saying it's A. So just as before, we now will have the same argument, and I'm just copying that. If I take out the common factor, because each of these sides are equal to A, so we take out a half A is then multiplied by H1 plus H2 plus H3 is equal to A. So we get that the sum of the simply is equal to the twice the total area of the rhombus divided by the side. Obviously, it doesn't make sense to talk about a height here. So it's exactly the same argument. What does this tell us about, for example, a pentagon? If we have a pentagon with equal sides, would it be true for pentagon with equal sides? Anyone? You can respond in chat or you can respond verbally. Suppose we had an equilateral pentagon. Would the sum of the distances be constant? I see Ria says yes. Why?
Ria?
Why would it be the same?
Ria, can you unmute your microphone and then you can talk directly about your answer?
Can I answer on the chat?
Yeah, you just said yes, sir. Yes, but why would it also be true for an equilateral pentagon? In other words, a 5-sided polygon with equal sides. The answer is easy. We can use the same argument. Because all the sides are equal, we would again have half A, H1 plus H2, etc., until we have H5. It would be exactly the same argument. In fact, we can generalize this. Here's an example. I hope it is showing on your side. There is a little button at the bottom. Equisided pentagon. Here we have an equisided pentagon. Notice that for an equisided pentagon, it does not need to be regular. As you can see there, it's not regular. All the angles are not equal, but all the sides are equal. Okay? And if we look at the sum of the distances to the sides, it changes, but notice that the sum of the distances remain constant. So this theorem of Viviani generalizes to any equilateral polygon. In other words, any polygon with equal sides. It can be a hexagon with equal sides or a decagon or whatever. we can use the same argument as we used here by writing it the sum of all the little triangles into which it is subdivided would equal the area of the whole triangle, and then the argument would exactly be the same. So I think that is a very nice generalization of Viviani's theorem that is easy for even primary school children, I think, to follow and understand. I think I will stop there. There are more explorations that perhaps you can explore on your own at home. You can see there are quite a few further explorations. And there's also, at the bottom here, there's, oh, that link there won't work. But if you go to my website, you will find this clues conjecture. If you want to explore further, it is on my website, but that link is no longer valid. That particular site no longer works. I think I will stop there so we can have some discussion or questions if you like. I'm open to whatever you are interested in to ask.
We still have 1 hour for the.
Would you like me to continue
Yeah,
with the
please.
same activity? We can. I wasn't sure if we were supposed to continue with the same activity. Shall we continue with the same activity? If people said, I'm happy to. Shall we continue?
Yes.
Okay. Okay. The next activity, number 3 there on the work, is open the paradistance.gsp. In other words, now we will look at where should we locate P in a parallelogram to minimize the sum of your distances to all 4 sides in the parallelogram. Okay, now let's go to a parallelogram, which here we have a parallelogram. Now that will probably not display on your side. Is it displaying? Is it displaying? Oh, it is displaying on your side. Okay, good.
Yes, it is now displaying the parallelogram.
Yeah, okay. I was just worried that we had the same problem as last time, but it's on the same sketch, so that should work. Here we have a program. Notice it is not a rhombus anymore. I can make it quite long. Of course, I can turn it into a rhombus if I dragged it so all sides are equal, but it doesn't have to be a rhombus, as we can see there. Here we have the measurements. The measurements are very small on my side. Let me just make them a little bit bigger. It might be small on your side as well if you have it in front of you. Let's make it 16. There are the measurements, and here is the sum of those distances, which are indicated there. What happens if I move P? What do you notice? We notice, just as before, what about the sum of the distances? It is constant, correct?
Yeah.
Just like we had before.
Yes.
But there's a difference here. All the sides are not equal. So why is it true in this case? Why for a parallelogram is the sum of the distances also constant? Because now we don't have all sides equal. Clearly, we know this side is equal to that side. AB is equal to CD, and we know that this side here is equal to that side there. AD is equal to BC. For a parallelogram, we can see it. But all sides are not equal. So how are we going to explain or prove that this is true? Would you like to think a little bit about that?
Can anybody respond? Why is it still constant, although the sides of the parallelogram aren't the same for equal to all sides of the parallelogram?
Clearly, this argument won't work. That we earlier. This thing is, if we think of the rhombuses one, this argument won't work for the simple reason let me just put that back in here. This argument won't work even if we divide it up into triangles. I will just draw one triangle there, construct a triangle interior. So if I have the 4 triangles here, we have the problem that only this side is equal to that side. So what we would have here, I hear people talking there. Does somebody have an explanation? But clearly this argument won't work here. If we, I'll just construct another triangle there. Clearly we now have a problem here. It's only these 2 sides that are equal. So we would have, for example, we might call this side A and that A, and this would have to be B and B. So here we would have a problem. We would have half A, taking it out, with the sum of those 2 distances, and similarly on the other side, half of whatever we call this A times the sum of those 2 distances. So this argument won't work. Let me just make that red to show that it won't work. It won't work.
We need different equation for two other triangles, 2 other small triangles.
Let me give you a hint. Let me give you a hint. If you consider these 2 sides, okay, these 2 sides, and I'm going to click on P now. Just think about this distance plus that distance. What can you say about this distance plus that distance? Whatever we would want to call it. What can you say about this distance plus that distance? Any thoughts on that? The height of the parallelogram, yeah, I wouldn't call it the height of the parallelogram, but it's just the distance between a pair of opposite sides. Do you agree? And what can you say about this distance between a pair of opposite sides? Let's suppose we call the one distance, argument's sake, H1. Ooh, that's very small. I'll increase the size now. Let's make that a little bit bigger, make that 24. Suppose we call this distance H1, and let me just And let's suppose we call the other distance h2. What can you say about h1 and h2? You said the height, but well, it's not really the name that I would give to it. What can you say about h1 and h2? And why? Well-
Is H1 and H2 constant?
Yeah. Here we have h1 is the distance to n. Okay, let me just increase the size of the labels there as well. I don't think they are too clear. Let's make that at least 80. Okay, for the distance from P to N is that, and the distance to J is this. So if we add these two, what do we notice? What should we notice? And why? The important question is why. The sum of those two distances is always constant. Why?
Is it right? It will be the height of the parallelogram.
Yeah, it's just the distance. I wouldn't call it height. I would just say it's the distance between two parallel lines. Remember, this side is parallel to this side. Okay? And what do we know about the distance? Remember, this is perpendicular and that is perpendicular. So we're really talking about the perpendicular distance between two lines that are parallel. And that is one way in which we sometimes define parallelograms, saying that it's lines of constant width. They are always the same distance apart. They don't come closer together or they don't go further apart. So this is really just the distance. I wouldn't call it height, because otherwise, this would also be height. And if we move to other figures, then it becomes a little bit meaningless. It's just the distance between a pair of parallel lines. Now, similarly, and this is where the proof is already done, really, because let me just copy that one and I will paste that in. If I call this distance h3, whoops, let me just correct that. And I call that distance from P to this side, I will call that distance h4. What can you say about that distance? Well, for the same reason as those two are constant, this must be constant. Oops. The sum of these two. So we have that h3 plus h4 will also have to be equal, no matter how we move this up or down. Because why? Because it's the distance, the total distance between two parallel lines. Now, obviously, to make the argument a bit more rigorous, we actually need to prove, let me perhaps indicate it here, we need to prove that these lines are actually straight. And that's not hard. I will just very quickly say how we can prove that. If we draw a line here parallel to that one, let me perhaps do that. I will draw a line here to that. Then it's quite easy, because this angle is 90 degrees. This one is 90 degrees, but we've constructed this parallel to that. So this angle must also be 90 degrees. This one must be equal to that one, because this line is parallel to this one. So these two angles must be 90 degrees, therefore this must be a straight line because it's 90 plus 90. Technically, we need to prove that that is a straight line. But that's easy to prove, as you can see. I'm not going to write it down. So really the argument here is just that H1 plus H2 is constant. Why? Because it's the distance between a pair of opposite sides. H3 plus H4 is also constant because it's just the distance between a pair of opposite parallel lines, parallel sides. Okay, and when we add two constants, because if this is a constant and that is a constant, if we add 2 plus 3, we get 5. We don't get a variable. So if we add two constants, we must get another constant. So that is really a proof. I'm not going to write it out. Can we generalize it further? Can we generalize it further? Well, any suggestions for a pentagon, a hexagon, octagon? Will this work? Well, clearly to have the result work, we need to have pairs of opposite sides parallel. So it needs to be a polygon with an even number of sides. So the next one we should look at would be a hexagon. Okay, so what do you think about a hexagon? I think I might have a sketch. Do I have a sketch? Oh, it doesn't look as if I have a sketch. Okay, I will probably, yeah, let me open up a new one, but I will have to share that, otherwise you won't see it. Let me share that as well. Screen sharing, new share. So I have those three and I want this one as well. I'm getting better at this, I hope. Okay, do you see the blank screen there now?
Yeah, the blank screen.
Okay, let me now construct a hexagon with opposite sides parallel. I usually ask my students to do this because we have a lot more time. We have a full semester doing these explorations, and they are more experienced also with the software. I will simply illustrate it here. With a hexagon, we want 3 pairs of opposite sides parallel. With a parallelogram, we have 2 pairs of opposite sides parallel. Now, with a hexagon, we have 3 pairs of opposite sides parallel. So there's my first side. Now I want to construct a side parallel to that. So I construct a point outside that. I select the point and I select the segment and I go to construct menu. You can do the same thing in GeoGebra. Sorry, I construct a parallel line to it. I will construct another segment here, say, and I will use this point outside that. The point is selected and the segment, and I will construct another parallel line to that one. So we now have this parallel to that, and we have this parallel to that. Now we're almost done. I can simply connect this with this line here, and now I need to construct a line here parallel to that one. And maybe I can just make it look a little bit nicer, oops, by dragging this one a little bit, or let me change there we are. There we have hexagon with opposite sides parallel, and maybe I can just hide some of these lines a little bit by just doing that. It's very quick and easy to work with. The software is really fabulous to explore geometry results. So there we have a hexagon with opposite sides parallel. Because I've constructed them parallel. You should see that they are parallel. Notice that opposite sides are not equal necessarily. Okay, in a parallelogram, if we have a quadrilateral, if opposite sides are parallel, then they're also equal. That is not true for a hexagon. We can have a hexagon with opposite sides parallel. You can see these two sides are not equal in length. This one is not equal to that one. This one is clearly much smaller than that one. I mean, I can change the distance quite substantially, as you can see there. I can, well, maybe can I? No, I can't drag that one. There's some limitations. Now you can drag, but I can see this one is much smaller than that one. The issue is here, what about the sum of the distances? Well, clearly, if we put a point P, whatever we want to call it, inside, we have exactly the same thing. The distance from here to there, I will maybe just construct that. And I've drawn a perpendicular from here to there, but notice it is also perpendicular to this one here. I will just add in little 90-degree markers there. And what can we say about this distance here? Now, where's my palette? There's my palette. Oh, something strange is happening. It's frozen. This is strange. Yeah, something is frozen here now, I'm afraid. But anyway, if we call this, can you see my figure there? If we call this distance H1 from this point to the side there, and if we call this distance H2, then clearly H1 plus H2 must again be constant. Why? Because it's simply, you called it a height, but it's simply the distance between a pair of opposite sides. You're welcome to call it a height if you like the term. You could say it's the height between two parallel sides, but I personally, I prefer just to say it's the distance between a pair of parallel lines, because that remains constant. And the same here, the distance from here to there, plus the distance from here to this side, that has to be constant as well, because this is parallel to that, and we know parallel lines never intersect, so the distance between them remain constant. And the same here, the distance from here to there, plus the distance from here to there, it doesn't matter where I move the point. At the moment, I can't even move it. Something is frozen on my side. I'm not sure why. But anyway, that distance will remain constant no matter how I move it. So we also see that this result generalizes for Vianney's theorem. We see that it generalizes to any 2n-gon. I wonder if it's frozen in the other. Oh, my window is not even coming up. Something is frozen completely here on my side. Perhaps I need to quit. It's not even allowing me to quit at the moment. Okay. Yeah, for some reason I have a beta version of a new version of Sketchpad. It may somehow it has now encountered a glitch. But we can see here the para distance, explain your observation, and generalize to polygons with a similar property. Well, obviously we can now generalize the result to any 2n-gon meaning that it is a polygon with even sides. So I say 2n-gon, so n can be 2. 2 times 2 gives you a quadrilateral, 2 times 3 gives you a hexagon, 2 times 4 gives you an octagon with opposite sides parallel. The result would hold in general for that. The result also holds, and I'm not sure this is going to work now because it seems my sketchpad is not working at all. Perhaps I should try and quit. Strangely,
Is that because you open too many windows, probably?
yeah, perhaps it shouldn't normally be a problem. I'm just going to quit Sketchpad and reopen it. I'll have to share it again then, I presume. Just give me a moment. There we are. Let me open that again. Okay, now let me share that because now this won't be on there. Sketchpad distances. There we are. Share. Is it back on again? The same. There we are. Okay. Now, I'm not sure what has happened there. Yeah, so the result generalizes quite nicely to any polygon with opposite sides parallel. But it has to be an even-sided because it doesn't make sense if we have a pentagon, because then you don't have the pairs of parallel sides as you do in a parallelogram or an hexagon. There's one last example I would like to do with you since we have a little bit of time. You will see there's one called open equiangle pentagon.gsp, which shows a pentagon with all angles equal. Where should you locate P in an equiangle pentagon to minimize the sum of your distances to all 5 sides in the pentagon? Well, I have a sketch. If you go here, you will see at the bottom, there should be a little tag that you can access, which says equiangle pentagon. And if you click on that, it should bring up a window that looks something like this, with a little bit of text there. That's just for fun. It's about a little article I wrote once. Well, here we have an equiangle pentagon. Let me perhaps indicate the angles here. All these angles have been constructed so that they are equal. So I will just quickly measure them to show you that I didn't cheat. There are the 3 angles there. The other 2 are also 108. Of course, this is true in a regular pentagon, that the angles are 108. But here we have an irregular pentagon with all angles equal, but notice not all sides equal. This usually also comes as a surprise to many of my students, I should add, because many of them kind of think that have all angles equal, then all sides also have to be equal, which is not the case, as we can see here. What is the sum of the distances? Well, you might guess that as we before, let me just increase the size there of that. Let's make it 18. We can see there that the sum of the distances also remains constant. Why is this the case? Well, this proof is a little bit harder. Just to save time, I will click on the hint here. And the hint is simply placing an equilateral pentagon on the inside. can you use this hint to prove why the result is also true for an equiangled pentagon? I'll make my screen a little bit bigger so I can maybe type the proof in there. Does the hint help? Anybody? Remember, I've placed a regular pentagon here. Okay, this one is not regular, the big one on the outside. But I've placed a regular pentagon here. What do we know about a regular pentagon? We've already proved that if we have a regular pentagon, the sum of the distances is constant.
Yeah, the same side.
Yeah, this distance plus that distance plus that distance plus that distance plus that distance. Let me pass, even if I move it a little bit to one side, like that. This distance plus that distance plus that distance plus that distance plus that distance must be constant.
Yes. Yes,
Okay,
constant.
why? Why? Well, we've proven that if we have an equilateral pentagon, the sum of the distances are constant. We've already proven that.
Yeah.
So if this distance plus this little distance plus that distance plus that distance plus that distance is constant, what about the outside distances?
It is the distance of two parallel lines.
Correct. I've placed this pentagon so that this side is parallel to that. So all we really have here is that this distance will be constant because these two lines are parallel. So this distance won't change. Little distance from this side to that side, because it is parallel, that won't change. And similarly, sorry, the distance from here to there, from here to there will be constant, and this distance. So what we have is that the sum of these distances, whatever we like to call them, plus the sum of all the outside parallel distances will be constant, and therefore we have proven that in this case the sum of the distances is constant, as we have seen there. Okay, so this is quite a nice extension also of the result. So the result also generalizes to any equiangled polygon, which is perhaps surprising. Yeah, there are a few more things I can say about Viviani's theorem. It can also generalize to 3D space, but the software that I have to illustrate that, unfortunately, does not run on this computer, and I think perhaps it is time to open up the floor for questions or comments if any of the participants have questions.
Okay. Yes, we have 3 minutes for question and answer session. So please, anybody wants to respond, giving comments, or ask some questions about several tasks that we have done with Michael today. Anybody?
I'm not hearing.
Yeah, Mr. Safrudianur.
No. Is the question about the task or about the sketch part? Because I am to I'm interested with the Sketchpad.
It is freeware now, the software. You don't have to, it used to be to have to buy the software, but it is free now. I gave the information to Dr. Budi.
Okay.
Has he shared it with you already? The information on how to download the software
Yeah.
Yes. Yes. So
and
it is
install it.
free for forever, right? Free
Free for?
forever or a long time?
Yes.
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 The
yes.
license of the app. Can we use it forever?
Yes, exactly. Yes. Yes.
Thank you
it
very
is-
Thank you very much.
It is forever. Yes, it is not like, I know people ask that question because like Word, for example, you have to renew the license every year for things like Word. No, it's forever. Yes, you can use it for always. Also, if you search on the internet, you may find available lots of free sketches. Perhaps I will share with Dr. Budi a few links. There are a few on my website, but I think if you just search free Sketchpad sketches, it will probably take you to the original site where there are quite a lot of sketches available, some that deal with algebra, some that deal with exploration of functions, some that deal with the teaching of calculus, some deal even with Boolean algebra, which is a topic that I've taught. So one can actually incorporate things like Boolean logic within Sketchpad, and all of those are available for free now. But I will send a link to Dr. Budi. I don't want to now go and search on the internet myself. I will rather give it to him and he can circulate it to all the participants.
Yeah. Thank you. So everybody now in the workshop can use the app freely forever for teaching and for learning and everything. Any other question about the task?
Perhaps if I can just say something. Unfortunately, my book, Rethinking Proof, from which this activity was taken from, is not yet free, which I don't understand why the publisher, because they've made the software free, you know, the software is free, but
So how do we get the copy of your book?
sorry.
I mean, should we?
Well, I would like to give you a free copy of my book, but technically I'm not allowed to. Perhaps I will communicate to Dr. Budi privately in case somebody from the publisher is watching.
Okay.
Okay. Yeah, I mean, I think it is just silly. I'd be happy to share it for free. I mean, by now. So, yes. But I will rather discuss that with Dr. Budi privately. Okay.
Okay.
Any other questions? There are numerous other books as well that were written specifically for Sketchpad, and all of these curriculum materials are not yet free. And I presume at some point they will be made available for free, but for some reason the publisher, McGraw-Hill, who have taken over from Key Curriculum Press, haven't yet given the authority. And I've been emailing them I won't say every month, but every few months I email them and said, have you reached a decision? When are you going to make it available for free? Yeah, they haven't gotten so far. So yeah, it's a little bit annoying for me because I would like to share my work and activities that I've used for many years with others. But it will hopefully come, that all the other materials, there are several books. But anyway, I will speak to Dr. Budi about mine privately.
Thank you very much for providing us the facilities. We are happy enough with this sketchpad that we can use freely forever.
Okay, that is good news. By the way, in Sketchpad, you will find under the help menu of Sketchpad right at the top, you will find that it says Sketchpad help. And underneath it,
we can't see your menu bar. We cannot see it.
Oh, okay. But you will find in the version that you have that if you go to the help menu in Sketchpad, which is on the top right of the menu bar, you will find that there's 7 tutorials that you can use that you through how getting to know the software better, so that you are able to do things like transformations, graph functions, create tessellations, and many other things. And I would strongly recommend that you do spend some time, especially with the first 3 at least tutorials, that you work through it carefully, because it is a little bit different from other software like GeoGebra, which a lot of people around the world use now, that you get acquainted with the functions and facilities of the software. So use the help menu. It's built into the program, so it is quite nice to have.
So we can explore ourselves in the help menu and find some tutorial and sample activities in the sketchpad. Okay, we're still waiting some question from participants of the workshop, or anybody wants to speak directly to Michael.
Oh, yes, I'm waiting for questions.
Oh, this one.
No.
Saprudi wants to give another comment.
No.
Or Leonardo. Uria Febriani. Oh, about the task, Prof. Michael. Ria asked questions about the task. The distance will be equal one side to other side if only it's parallel, or what?
Yes, for the Ria, when we looked at the case for when we have a parallelogram, or when we have, I wonder if that window is, I think that's where it froze. Or when we have a hexagon with opposite sides parallel, yes, this distance between the pair of opposite sides will only be constant if they are parallel. If they are not parallel, then the distance won't be the same. I mean, I can just quickly show you an example. Suppose we have 2 lines like that, and we have a point here, and I measure the distance from here to there. There's the distance from A to BC, and there's the distance from there to there. If they are not parallel, then the sum won't be constant. Let's just add them together. That plus that is equal to that. Let me just put it here. Let's make it a little bit neater here. I hope it's displaying on your side, okay? There are the two distances from A to BC is this distance. And A to DE is that distance sum. If they are not parallel, then obviously the distance will change. As you can see there, it will become smaller and smaller. Obviously, it will become zero where the two lines meet. The sum of these two distances will only be constant if this line is parallel to that line. Those two lines have to be parallel, or these two lines have to be parallel. Because that follows from the definition of parallel lines, or one way of defining them. If we have that this line is parallel to that line, now I've just roughly dragged them. You can see there it's changing a little bit because I haven't accurately constructed them. If I had it accurate, it would construct a parallel line. Oh, it says my internet is unstable again. And I will now just attach this to the parallel line. Now I've got it accurately. Once we have a pair of parallel lines, the sum of those two distances will be constant. Okay? Because why? Well, the distance, that's the definition. The distance between, or one way of defining parallel lines are lines that never meet. And what that means is that they never get closer and closer together, or not further and further apart. So the distance from this line to that one must be equal to this distance plus that distance. So that's a good question. Yes, that is a necessary condition for this result to hold. Any other questions?
We have another question from Nurzahwa. Nurzahwa? Yeah.
Yes. Can I ask, yeah, we have discussed it about the two-dimensional shape that we could generalize by sum of the area of the all small triangle inside the two-dimensional figure. Can we generalize to three-dimensional figure by using sum of all the volume of small interior pyramids?
Yes, exactly. If we consider a tetrahedron is in space the equivalent of a triangle in the plane. If we take a tetrahedron, I will just quickly draw a sort of tetrahedron here, but think of this now as a 3D object rather than, let me just make that a dashed line. So if we have a pyramid or tetrahedron like that, okay, and we now have a point inside that little pyramid, okay, then it would subdivide if we drop a perpendicular point to each of the faces. Now we're talking about the faces. And yes, the sum of the four pyramids that are now formed, the tetrahedrons, that would equal their volume now. So we're using volume. In fact, the result generalizes where we had, you may remember we had equi-sided polygon. Here we would have a tetrahedron where the areas of the bases, in other words, of the faces of each of the pyramids are equal. Then we can use the same argument because you have a common factor you can take out and you will have that the result holds. That is one way of generalizing it quite easily, yes. If like, yeah, it won't work on the internet, I'm afraid. um, the software that I have runs in Java, and Java no longer works. So I have it. I have a link here. Look here, generalizations of Viviani's theorem. Is that showing?
Yeah.
No, it's
Thanks.
taken a while. Generalizations of Viviani's theorem. You can use this link, or you just type in dynamic mathematics learning Viviani general. You will find there that there's a generalization on that page describing exactly this generalization, but there are others as well. One can also generalize Viviani's theorem in other ways to 3 dimensions, but that was well observed. Thank you.
That's interesting, Zahwa. Do you have another question?
Enough. Thank you, sir.
Okay, Nur, thank you.
We still have one more question from Leonardo. Yeah, Leonardo.
Yeah. Sir, I'd like to ask, how's the situation there in Africa if you teach proof and proving? We here in Indonesia, proof and proving are less popular here because from my last research, students said that they never learned about proof before. It's on high school students. Is it different or the same there? Thank you.
It is a little bit different here because we have geometry as a large part of our curriculum, as an important part. And students are introduced to proof in our curriculum, school curriculum, already in grade 8 and 9. And then they continue with proof until grade 12. So there's definitely more proof in South Africa, I think, than in some other countries, because we have a focus on geometry. But also we do some elementary proving, obviously with algebra, proving elementary number theoretic results using elementary algebra. For example, a trivial example, the sum of 2 odd numbers is always even. That sort of thing is easy to show using algebra. So that is introduced from about, as I said, grade 8 and grade 9. Very little, but from about grade 10, they are expected to do quite a bit of proof. I won't say we are very good in teaching proof. Our education system is very diverse. We have some excellent schools with very good teachers who teach proof very well. But then we do have schools where proof and even geometry is rather neglected, where there is not a lot of emphasis on that. So we do have a problem when students come to university that we have, and I even had that, I taught mainly senior classes in the last 20 years or so. But even with some of my senior classes, I found students of varied abilities. Some were excellent students who could write proofs quite easily on their own, and some other students I literally had to almost, take their hand and help them step by step. So it is a problem, I think, worldwide. I think the teaching of proof is not as good as it should be.
Yeah.
Okay.
Thank you for
may I ask a question of you, Leonardo? Do you how much geometry do you have, Euclidean geometry, in Indonesia, or is that neglected?
I think in high school we didn't learn much more about geometry. We just learned about the surface area, the volume, about that in geometry, but not the proving, because usually the teachers skip that part.
I see. Yeah, yeah. Yeah. So you actually don't learn geometry as a deductive system, in other words. Yeah.
Just
That's
the
very
formula.
different from South Africa. Yeah. In South Africa, they are exposed to to geometry, I would say, as a deductive system. From about in grade 8 and 9, it is more informal, although they do simple proofs in grade 8 and 9. But from about grade 10, it becomes much more. And in grades 11 and 12, we do quite a lot of theorems and proofs of riders in circle geometry. So we're one of the few countries that still focus on circle geometry and expect students in the final exam to be able to not only prove theorems in the curriculum, but also to prove results they may not have seen before. So I think that is an advantage in terms of students preparing them for university in some aspects.
Can I have some questions? So is proof also taught in your country starting in the beginning of elementary or in the middle, junior or high school?
It's in junior high school, in grade 8 and 9. It is not in the primary school, no. It starts in grade 8 and 9 and then becomes more rigorous and more built into the curriculum wherever it is possible. Yeah, so it starts in junior high school.
Also nice to know that your the curriculum concern and emphasize more improving. We have also, but curriculum in Indonesia, I think also emphasize improving, but more in problem solving rather than improving.
I see. Yeah. Well, obviously problem solving is a big component of our curriculum and a main focus. But problem solving within the curriculum usually, well, I don't want to sound patronizing towards our own curriculum. The problems usually are not of a very challenging nature, which is why in the South African Mathematics Olympiad, we try and encourage that across a wider range of students, where the problems are definitely far more challenging. We have had about 100,000 learners writing our Mathematics Olympiad. And we have used that as an opportunity to identify some of our mathematical talent that we can then run workshops with them to prepare them for competitions like the IMO and other math competitions. But that is at a different level. The problem solving within the curriculum is fairly elementary, I would say. I hope that it gives you some idea of our curriculum.
It is very nice discussion, but I am very to say that we come to the end of this workshop because it is already 3.5. So for the last remark, is there anybody in the Zoom wants to give some comments? Maybe the last comments about this workshop.
Me?
Okay,
Can I?
Safrudianur.
I just want to say that this workshop is very nice, sir. I like to. I'm very happy to follow this workshop. Thank you very much.
So
Thank you very much. I'm glad to hear.
Yes.
I'm also inviting all the participants to turn on the camera to take a photograph with Michael, and also you can unmute and give applause to Professor Michael from University of Stellenbosch. Thank you very much, Professor
Thank you.
Michael.
I appreciate it.
So can we have some pictures together, virtually, of course?
I have stop share screen first.
Oh yeah, the screen also.
Must I stop share
Yep.
on my side?
Thank you.
Okay, stop share like that.
So we are now in a gallery view, so you can see all the participants with you today. They are
Okay.
129.
Oh, okay. Yes, it's a pity that we weren't in the same room. I usually like walking around, seeing what people are doing, and it's not the same. At least I have a few faces up. It makes it more human.
Yes. So everybody please smile. So host bisa bantu. How many slides? Okay, 1, 2, 3.
Will you send me a copy of the picture?
Of course, I will send a copy to you to your email.
Thank you. Thank you, Dr. Winnie.
Okay. And
Okay, are we at the end then of our session?
thank you very much. Thank you for your great presentation, your material, and giving us insight to motivate students to learn about theorems in insightful and fun way. So wishing you good health and happiness during this pandemic situation. Thank you very much, Professor Michael. I hope that you can visit Indonesia some other time.
That would be wonderful. I would certainly like to visit. Thank you. And
Another big
keep
applause
up.
for Professor Michael.
Thank you.
Thank you.
Oh, I see I have a lot of messages. Thanks, everyone. Thank you. Bye-bye.
Bye.
Okay.
Bapak Ibu, mohon untuk masih di sini karena kita ada beberapa informasi tentang tugas untuk workshop. Pak Jerry bisa bantu menyampaikan?
Ya, Bapak Ibu, jadi sehubungan dengan tugas yang diberikan oleh Profesor Michael tadi atau sebelumnya, kemudian nanti juga akan ada tugas dari panitia, di mana peserta nanti mengerjakan tugas tersebut, kemudian dikumpulkan di link yang akan dibagikan. Tugasnya nanti akan dikumpulkan menjadi buku dan kita akan terbitkan dengan ISBN. Untuk para peserta nanti akan dapat bukunya ya, Ibu Tia ya. Dapat e-booknya, jadi dapat salinan e-booknya nanti akan dikirim ke Bapak Ibu yang sudah mendaftar hari ini. Google Scholar juga akan terindeks Google Scholar ya. Kemudian untuk sertifikatnya sekali lagi saya tekankan, jika Bapak Ibu sudah mengirimkan tugas, nanti sertifikatnya akan dikirimkan ke Bapak Ibu dengan keterangan waktu 32 jam pelajaran. Begitu ya Bapak Ibu, untuk tugasnya apa dari panitia nanti akan diinformasikan lebih lanjut melalui WA Group. Terima kasih, selamat sore.
Sore.
Demikian acara workshop kita pada hari ini. Sampai jumpa di acara the second acara National Conference on Mathematics Education and Workshop on Mathematical Proving. Semoga nanti kita bisa mengadakannya secara offline and online, of course. Terima kasih Bapak Ibu yang sudah berpartisipasi. Sampai jumpa. Kami dari panitia mohon maaf apabila ada kesalahan dalam penyelenggaraan acara ini. Terima kasih. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam. Waalaikumsalam warahmatullahi wabarakatuh.
Dari tadi aku
Tidak apa-apa. Ini nambah. Yang merah ya. Bapak Ibu yang belum bergabung di grup workshop boleh nanti menghubungi salah satu panitia. Kita sudah di akhir penutupan, Bapak Ibu boleh meninggalkan Zoom kita pada hari ini. Terima kasih.